This video is sponsored by Rigging Dojo, which offers training courses for rigging and technical art from veterans of the industry. Head over to Rigging Dojo to find more about it. Alright folks, so welcome back to this second part about MC GPU. So modularized GPU that can be together. In the first part we discussed the general idea, the methodology that Nvidia used to test all these things, and the final goal they had. Right, so after we took care of that and we discussed why it's important for the future, not only for GPUs but for CPU as well, now we're going to discuss three different architectural innovation optimization that Nvidia proposes in order to make this kind of architecture work, to try to compensate for whatever latency that might be introduced with this interconnect between different modules. All right? And in the case you're not really familiar with hardware architecture or GPU architecture, how memory works, the short story is you have caches, all right, in these processors or in these modules. So if you read from RAM, right, everyone can read from RAM, and you invalidate and you write to memory, it's not going directly to the RAM. You might just invalidate one cache line, all right? But what if then another module need that specific cache line now? It cannot read it from memory because you modify that in the cache, is not yet in RAM. So you basically need to transfer, you're invalidating that cache line and you're going to grab it from an addition, or from the neighbor, sorry, I cannot spell that word. All right, so that's why you need a ring bus to make them communicate. So you can grab this memory or from any of the neighbors, all right? But of course, if you are on this processor, you need a cache line from this one, right? You need to make two hops, right? The bus needs to travel longer than just the neighbor one. And going back right to DRAM directly and then we read from DRAM is no, it's ridiculous expensive. Reading from RAM is like 600 cycles on a GPUs. So you need to limit that. So we're going to see how Nvidia decide to try to limit these kind of problems, all right? So the first thing they're going to do is revisiting the cache architectures, like how can we cache as much data as possible without impacting performance or actually improving them, all right? So their core idea is to add an extra level of cache, all right, called L1.5, and that's a dedicated cache with a specific purpose. Sorry. So the purpose of this cache is to go and cache only the reads that go through the bus. All right. You can see here there is a streaming multiprocessor, and here there is the X bar bus. All right. So whatever needs to be picked from a remote is going to be cached here. All right, so if you need to read that multiple times, you're not going to pay the price to transfer that multiple times. You have a dedicated cache just for that. Now, they try to see where do we get the transistor from to generate this cache. All right, so they evaluate several things by shrinking the L2 cache in different proportion, or dedicate new transistor, completely new transistor to build this memory. All right, and so here they decide basically to split in a fashion way. So isotransistor, meaning that you have a 32 megabyte L2 cache, you split it into 16s, all right? Or what they're going to do here, they're going just to take 8 megabytes to generate the L1 cache, or the next test they do is like, okay, fuck it, we are going to create a new but has 32 megabyte L1.5 cache. All right, so these are the results with just 8 megabyte, and that's for memory intensive. All right, so the kind of workload that will benefit a lot from this. 8 megabyte L1.5 cache, they only get 4%. All right, 16 megabyte, they get 8%, and with a 32 dedicated, they get 18%. All right, so they decide to go with the middle ground, 8%, which doesn't require adding any extra transistor. All right, that doesn't mean they might not decide to add those in the future, but they try to basically keep the budgets for transistor fixed. All right, because they know they can build with the current budget of transistor. So if they can stay in that budget, there is no manufacturing problem whatsoever. All right, at least related to transistor count. They also check for application with small power level or high compute level. High compute level is pretty much not affected. It's not really affected because, like, if you have a lot of compute, inherently means you don't access much memory. So you grab some data and you do a lot of computation on that. That's what the GPU usually likes. So that's the first kind of optimization. If you want to see all the tests, feel free to read on the paper. I'm just covering the most important ones. At least I believe they are most important ones. So next, they want to change the scheduler. All right. So the scheduler is basically the hardware that decide which part of the hardware is going to process the job. All right. If you don't have any GPU computing or programming on your back, the core idea is you have a problem, you split this problem in several pieces, and different block of cores on the GPU work on that piece of the problem. All right. And of course, that's a super simplified, and a seasoned GPU programmer won't be happy with my explanation, but this is not a GPU course, so I'm just trying to keep stuff simple. But that's the thing. So the scheduler decide, all right, streaming processor 1, you're going to work on this chunk of problem. Streaming processor 2 on this chunk of problem, and so on. So how it was working previously, they mention it here, is round robin order. All right. So it will start from streaming multiprocessor 1 and will give a chunk of work. Then streaming processor 2 give you a chunk of work, 3, 4. Then when it's done, so it doesn't have any more streaming multiprocessor, it start again from 1 and say, hey, are you done with what you're doing? Yes, I give you more work. You don't? Oh, all right, I will pass by later. And it goes on. So you have no guarantees that the jobs are allocated consequently, one after the other, like you see here, right? For example, it start allocating consecutive jobs on different, in this case, modules or streaming multiprocessor, but that doesn't happen anymore. Here, you get a different kind of layout, maybe because the streaming multiprocessor were busy or the scheduler make different decisions. So before, you had no guarantees on what they were going to do. And roughly, you were going this sequence kind of behavior. And some papers, like the StreamScan, kind of try to exploit that, but that's a whole different story. So that's how it was before. So they want to change this to basically allocate consecutive chunk of the problem on the same GPU module. All right. So you can see here, the array, basically the block of threads, are consecutive for each GPU module. All right. Kind of like, let's give you a stupid example. So you have a mesh you want to process. You have 2,000 vertices, and you chop that into 100 vertices each. And of course, that wouldn't work well in the GPU. You need multiple of 2, probably a bigger chunk, but that's not the case. So that's not what we're talking about. But you chop a piece of 100, all right? And in this case, it's going to allocate 4 consecutive piece of job on the same module. So it means that module 0 is going to work from vertex 1 to 100, then 100 to 200, 200 to 300, and 300 to 400. And the very reason they do that is because they want to exploit data locality, because they hope that consecutive jobs, they're going to share a lot more data than this round robin order would. All right? Because you see here, CTA A, CTA B, B plus 2, CTA D, they might work on completely different subset of the data. So you're trashing your cache between one chunk and the other. So they hope that between one chunk of work and the other, you're gonna hit a lot more caches. All right, you get a lot more cache hit. So that's what they hope. And they see a decent speed up. All right, so for memory intensive, combining the L1.5 cache and the array, so the new scheduler, they get like 23%. Then for computing, you see not much, 1.9. For computing intensive application, again, that's not big deal because you don't manipulate a lot of data. You just do shit tons of computation on that. And again, on low parallelism, you get a 5.2, all right? And you can see that those two features work well together, all right? Because you try to reduce the actual memory you need to fetch at random or from different modules by using this array allocation. And if you actually need data from different modules, you have your lovely L1.5 cache there trying to help you. So working together, you actually get a nice boost. And finally, the last bit of data is called first touch. Last piece of improvement is called first touch. And basically what they want to do is to try to allocate memory pages directly into the module that access it first. All right? So basically partitioning data on different modules based on whoever requests them first. All right? So as this, and really one important thing that they mention here, all right, is that they allow in this way, so the combination of the CTA, the new scheduler, and this technique, the first touch, allow the memory pages brought to the module memory partition to continue to be local across subsequent kernel launches. And you might wonder, why do I care? Because a lot of kernels, all right, a lot of problems are actually solved through iteration, all right? So you apply the same algorithm in iteration, one after the other. So for example, you want to smooth a mesh, you need to smooth the mesh, the whole mesh once. Then in order to smooth a second time, you need to be done with the whole kernel for the first run, and then you run a second. But if you can keep data locality between subsequent kernel launch, it means that when the second kernel goes and the same blocks of data get allocated to the same module, your data is already there. You don't need to fetch from RAM, all right? You're gonna hit the cache and you're gonna be much faster for subsequent kernel runs. So that's really, really important, all right? And they try to show you here, right? So the CTA 0134, they get always assigned to that module, all right? And again, all this works nicely together. And you can see here from this table, all right? So here, the first three columns are the single feature applied in isolation, all right? So the L1 point cache in isolation gives you some decent boost. The distributed scaling gives you nothing, all right? And then the first touch, so the new memory partition, actually makes your car slower, all right, if applied in isolation. But if you put all those three together, you get a massive boost, all right? So the memory partition that it was a loss before applied together with the new CTA scheduler and the L1.5 cache, you get a massive boost, all right? And so all those three features, they work synergically really well together. And that's allowed them to get a monolithic and an MCM GPUs a fair close bit together, all right? And that's about it. So that's conclusion. Some more talk about efficiency. You can read through that. There is no any major topics covered there. So that's really interesting to me, and we are gonna benefit from that a lot if they actually going to start producing this way, which I think they will, because Moore's law is almost that. Shrinking the transistor is much harder. Cramping more transistor is getting harder and harder, right? Because you might wonder, right, who cares? Even if expensive, just make a bigger car, a bigger die, keep growing it, fuck it. No, that's not gonna work, because for the photolithography, so basically the thin carving with lights in the silicon, it has a reticle, all right? That reticle is basically the size it can work on. And it has a limit, it's a physical limit it cannot go above. So it's not like you can make a square meter CPU or GPU, right? That is ridiculously fast. You can't. Physically is impossible. Without even talking about the other problem we mentioned in the first part of the video, all right? So this is really important. In the CPU land, thanks to AMD, that's already happening. And they make it work really well. If you actually go and read about epic scaling, I don't want to make a pun, but let's say it's really good. The scaling is almost linear, all right? I think that they have like 90-something% scaling, which is crazy, all right? So the Infinity Fabric is working really well. All right, so that's what I wanted to cover. I hope this information was useful. Let me know what you think about this trend, this change in hardware architecture, and of course let me know if you actually would like such a big fat GPUs, because I know for sure I'd love to have one, or